I/O 2016, right? Oh, come on, we're done clapping now? Is that it? All right, we're done. Hello, everyone. How are you doing today? Good? Staying out of the sun? Yes, fantastic. Hey, I want to thank everybody for being here. My name is Colt McCandless, and I got to tell you, I love Google I/O. I love Google I/O because this is the one time during the whole year that the crazy Googlers get to talk to all of you all about the weird stuff we do that we can't talk about the rest of the year. And that is fantastic, right? And today we're talking about something that's so near and dear to my heart, and that's data compression. It is by far one of my favorite, most obsessive things that I ever get involved with. And I'm so happy that all of you are here and all the people standing outside. I'm sorry there's capacity issues. We'll give them a t-shirt or something later. But really quick, before we begin, I gotta tell you, we've only got 45 minutes today. And that is just not enough time to get through all the awesome, crazy image compression content that we need to get done. So over the past couple weeks, I've been trying to diffuse some of this stuff to some other places. First off is my medium.com page. Has anybody been reading these articles? Yeah, round of applause if you've been reading the Medium articles, yeah? We're live, folks. You gotta make them hear it, yeah? If you read these articles, we get into a lot more depth on how some of these image formats work and how to make them a lot smaller. Second off, of course, is the Android performance patterns videos. Anybody watch these? Thank you, thank you. Thank you. That's fantastic. Now, if you've ever been interested in data compression, if you've ever tried to make an attempt to understand the algorithms, but found that the math is really weird, or it's too gnarly of a concept, or maybe it's not presented in the right way, then good news for you, because Alex Hackey and I have actually got together, and we've actually written a data compression book. And we took a different approach to it. We threw out all the math. All of that crazy, gnarly stuff that makes your brain melt, we got rid of it, and we reapproached how we should be teaching data compression to modern developers and engineers. So if you're interested in deep, fundamental understanding of how to make your apps smaller for users, check out this book. Deal? Deal? All right, business is out of the way. Let's get started. So when we talk about reducing the data sizes of your applications for your users, there's generally two buckets that I like to think of. On one side is your APK size. And this includes all of the stuff like code sizes, language information resources, image resources. We've got layout data, config, blah, 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 blah. All of the information that's zipped up into a single APK file and downloaded when users install your application. Now, on the other side of things is all of the other stuff that your app downloads once it's installed from the internet, right? So this could be many, many, many things, but it mostly boils down to images and serialized data. Now, I gotta say that the APK stuff, making your APK smaller, is a whole deep and crazy domain that we're not gonna get into today. However, if you stay in your seats, the next session will go very, very deep into that subject. So make sure you stick around for that. One thing you notice here, though, is that images actually show up in both of these categories. And that's why we're focusing on images today, because quite frankly, images are awesome, right? Round of applause for images? Yeah? I promise you I will ask you to applaud weirder and weirder stuff as the talk goes on, right? Like, who likes gummy bears? Yeah, there we go. We have to have an understanding as an audience and a presenter. That's how this works, right? Images are fantastic. We use them in our applications. We convey emotion and power and information and all this other great stuff. But images also have a problem, is that they're easy to bloat. They're easy to get too big and too many resolutions and too many pixels, and that causes problems for your users. Because bigger images take longer to download, which means that there's more bits on the wire, which cost your users more money to download them because they're on metered plans. And their cellular radio is on longer downloading the larger images, so you're eating their battery more. All of these little things add up when you start bringing these images down, which is why making sure that your images are compressed as good and as small as possible is super important to make sure that your users are having the best experience. And in general, there's a lot of different things you could do with images, but as Android developers, there's really only 4 data formats we care about: PNGs, vector drawables, JPEGs, and WebP. Now, the rest of the talk that we're going to go into today is going to be opening up each one of these formats, taking a look at how it works internally, and how you can squeeze out every bit of data from these things possible. Sound good? Sound good? Yes. Don't worry, you'll get the hang of the applause cues. They took down the sign that I asked for later. That's okay. All right, so let's start at the top with PNG files. PNGs have to be one of the most amazing formats in terms of Android development. They've been here as long as anybody has seen. They provide amazing quality and actually pretty good data compression. So let's figure out what's going on under the hood. So let's say we have an image. The way PNG compression works is that we take every row of pixels in that image, one at a time. We process each row individually, and what we do is we apply something called a filter to it. Now, the filter itself is basically a modified delta processor, right? So basically, it's going to try to subtract the current pixel in the row from the previous pixels or the one above it and do all this weird math. The point of the filter is simple. It wants to produce the most number of zeros and duplicate values possible. That's it. That's all it wants to do. The output of that is then fed into a very common, super everywhere encoding system called deflate. Anybody familiar with deflate? Get him a t-shirt. That's right, we'll get it to you later. Deflate is actually comprised of two main compression algorithms. The first one is called LZ77. If you've watched my compressor head video, then you'll know that LZ77 is a dictionary algorithm that tries to match runs of duplicate characters multiple times in a stream of data. The output of that is then tossed to a Huffman encoder, which is a statistical encoder. If you've ever been to CS 101, you've probably dealt with Huffman in some form. Now, this is, again, is done on a single line, and the output of deflate is then kicked out to disk. Now, what these two stages mean is very important. In areas of your image where there's very similar pixels, or there's a lot of duplicate pixels, that filtering stage is going to produce a lot of zeros. It's going to produce a lot of duplicate symbols, which means the LZ77 and the deflate stage are going to come through and basically make that stuff disappear. So areas of similarity are going to get great compression. However, areas of noise where there's not a lot of similar pixels, where there's different colors that may not be adjoined to each other, are actually going to have worse compression. And that's what you get with this trade-off of the filtering stage with the deflate stage, right? Now, with this in mind, we can obviously see a couple places that PNGs can be optimized a little bit more, right? The first, of course, is less input colors. If we've got less input colors coming into the filtering stage, that means that we're going to have less unique colors coming out, and we're going to get better compression. The other thing is actually smarter filtering. I won't get into it right now. There's a different post on it, but there's like 5 different filtering modes that the encoder can choose on and all that other stuff. And there's a lot of math and accelerations that go into finding that in a way that's not going to take 10 years to compute it. The other thing is a better deflate algorithm. Believe it or not, deflate isn't the best version of deflate. There's actually more modern deflates out there, and applying those to the algorithm actually produce smaller files. And finally, removing chunks. And that's actually a tricky one that I'll get to in a minute. But I know what you're saying, like, hey, wait a minute. All of that stuff should be happening for me, right? I mean, there's this really cool tool in the Android toolchain called AAPT. Anybody heard of that? Round of applause, yeah? Yeah. I mean, in reality, this should be doing all that for you, right? It should be crunching your PNGs down as small as possible. Anyone seen that happen? Nobody? Some people? Someone's asleep already. One applause. Get that guy a t-shirt. T-shirts for every clap. So I want to point out that while the AAP tool is there to actually try to make your PNG files smaller, it doesn't do everything it could. AAPT tool does 3 things specifically, no more, no less. The first thing it does is analyze your PNG files to see whether or not you're only using grayscale colors. So for example, if your red, green, blue channels are all the same color, it will actually make your entire image into single 8-bit alpha channel. That's it. Goes right down to grayscale. The second thing it'll look for is whether or not you're actually using your transparency channel. If you've got a fully opaque image that's not using any transparency bits, it'll actually get rid of that entire channel and save it out to be smaller. And the final thing, and this is the one that's pretty awesome, it'll actually scan your entire image and determine whether or not you're using 256 unique colors. If you're using 256 unique colors, it'll save your image in a paletted format, which basically decreases the size by some insane amount. Right? Basically, all of the 32-bit per pixel data gets quantized into a little table like that we call a palette, and it's replaced with an 8-bit pointer into that palette. So instead of 32 bits per pixel, you're now down to 8. Good savings, right? So the question that I have, though, is, okay, AAPT is really good, but how good is it? And to answer that, I had to open up an application and take a look at how AAPT was impacting and affecting that application to see whether or not it was doing a really good job or if there's some improvements to be made. So being I/O, I felt maybe we should do a callback to last year's IOShed application and see how well AAPT was doing with that. So anyone look through the source code of the I/O scheduler application from last year? Round of applause. Yeah? Good. Did anyone find the hidden Easter egg in the source code? No? Oh. Then forget I said anything. So when we open up this file, there's a lot of assets. Now, there's two things to compare here. Of course, first is the source code files in GitHub, and then there's the APK that you can actually download from the Play Store, unzip, and take a look at the assets, right? So I wanted to look between these two, because if AAPT is doing a great job, I should see a big change between those two file sizes, right? So I opened up the file, and I just picked some random graphic. This was the one I happened to look at. That's a 144 by 144 pixel PNG file, and that's 6K. That's huge, right? Sorry, this is in the source code repo, right? Now, when I open up the APK and take a look at it, it's actually only 2K, which is better, but still way too big for 144 by 144 pixels. Like, that's massively huge, right? And so I said, well, hold on, something's missing here. Obviously, we got some optimization. Let's figure out what's going on. So I opened up this image in Photoshop, and I saved it for the web. There's a difference between file save and file save for web. There's a whole different process in there. In that process, I actually quantized it to only use 256 colors. And you can see when I did that, we got about the same size as was in the APK. So we can see that, hey, the AAPT did its job. It probably quantized this to an indexed image, right? But here's the problem. Take a look at that image. Does it look like it's using 256 colors? No. So let's crank it down a little bit. Here's what 64 colors looks like. Anybody see a change? Let's go even more. 32 or 16 colors. Still don't see a change. 8 colors. Still don't see a change. Or if you do, your eyes are better than mine. The point here is that we went from 256 unique colors down to 8 unique colors and didn't see a change in visual perception. The difference in file size, though, was huge. Right? Because we were able to find a smaller color size. So let's look at a different example here. So this is one of the big banners, big banner images that you see inside of the application. That's 49.5K in the GitHub repo and 32K inside of the APK. So again, there's some smaller modifications going on here to the AAP tool, but still, let's see if our trick works here too, right? So let's actually down-res it to 32 colors. This one isn't that good, right? I mean, you can see some banding in the gradients there. You can see that some of the colors just aren't looking as true as you can. So let's bump that up to exactly 256 colors. Here, you can't actually see any visual difference, right? But notice the difference in the file size. This is only 18K instead of the 36K, right? So this image actually only needed 256 colors, but maybe the source image didn't have that. And this is the problem with the AAP tool. It does a great job of those exact 3 things and no more than that. So in the first case, we had an image that obviously needed less colors, right, and could have been optimized more. And in the second case, we had an image that had maybe just over 256 colors, that if we set it to 256, it still would have looked fine, right? AAPT does neither of these for you, which means that it's your job as a developer to step past that and start doing additional methods to reduce the size of your PNG files. So let's take a look, as I said before, how easy it is to mess this up. So you've actually just take a 16 pixel by 16 pixel all red PNG file save as from Photoshop. You look at 2K. That's 64 pixels. That's 2K. The funny thing right now is everyone in the room is doing a gut check about whether or not their designers are using file save as from Photoshop to save their PNGs, right? Right? When you save it for web, though, you end up at 121 bytes, which is better, which is obviously better. That's the thing we want to see. This is how easy it is to mess up this problem. Now, the good news is, though, that you don't have to go into crazy town with trying to optimize all those things we talked about before with the different stages of PNG. PNG optimization is an old problem. Old meaning the 90s, right? I mean, some of you were alive in the 90s, right? Okay, yeah. Well, who wasn't alive in the 90s? Okay, all right, yeah. Old people, nice. Sorry, professional people. Yeah. The truth is that there is a plethora of tools out there that have already been solving this problem for almost 2 decades. You don't got to do the heavy lifting. Just Google it and pick any one of these. Really, they all do different stuff and have different algorithms and different needs and different settings and whatnot. But if you just add any one of these to your existing asset chain, you're going to get an immediate reduction and an immediate improvement in file size. Now, that being said, there are some things that you can do to make it even better in terms of file sizes. And I only mention these 2 things because I'm seeing them a lot in applications that I'm opening and taking a look at. AKA, here's the things you are all doing that you need to stop. So first off is, if you can, in every single way, try to make your image 256 colors or less. It's a pretty simple quantization step. You just test it, you take a look at it. Here is one of our Google Doodles that we actually put on our main page here. You can see it came down as 24 bits per pixel. It wasn't indexed at 197K. When we exported it, the index mode is only 73K. Again, visual difference here, imperceptible. But the difference in file size was huge, just by trying to take into account hitting that indexed mark. And you can see the palette here is actually pretty simple. I mean, there's nothing crazy going on. By the way, that diamond down there on that white actually represents the transparent pixel color for that. And you can actually do a bunch of those. So, read the article. There's more stuff on that there. Here's another one. Can anybody tell me why one of these images is 139 and one of these is 214? Alpha channel, good. What about the alpha channel? Wait, did you read the article? Oh, wait, never mind. Cheater. No, I'm kidding. So it's absolutely right. Alpha channel. So here's what's happening. I've seen this quite a bit in a lot of the files I've opened. So visually, you can see that the last frame is what the user sees here. But when you open this thing up and you take a look at the RGB channels and the A channels separately, you can see that the RGB actually has a ton of data that gets masked out by the alpha value. The end result is the same visual image to the user, but to the compressor, we still have to compress all of that RGB data. The filtering stage still has to be run on it. The output of that still has to be run through a deflate algorithm. And because there's a lot of non-uniform pixels there, the result is going to be a lot of bloat in your compressor, right? However, if we try to pre-multiply this stuff and mask out the pixels that we know are never going to be seen, we end up with a much smaller file size. I've been seeing this in applications popping up lately a lot more than I'd like to say. So take a look at this. Now, one of the final things I need to point out, if you're going to go down this path and you're going to add in some of these awesome pre-processing tools to your chain and get it all working with Gradle, and you're going to tell your designers to not do that thing I just said and try to make index files, you may run into a really weird issue. So let's say we've got this great image. It's about 216K, and we actually run it through Zoffly PNG, which is a fantastic open source tool that is a better deflate algorithm compressor for PNG files. And we get it down to about 185K. But when you build it, it actually goes through AAPT and it bloats to 201K. The reason for this is that the AAPT tool doesn't know that you've pre-processed your image, right? Again, it's only checking for those 3 things. And so it's going to look at your image and it's going to try to make it into A, B, or C format, and then it's just going to save it right to disk. The problem with that, though, is that you may have made modifications, and obviously your version is smaller and their version may not be. To get around this in your application, you need to specify the option Gradle cruncher enabled equals false. This will disable AAPT optimization for all of your PNG files that are coming through your pipe. Now, the problem, though, is that once you do this, it's kind of on you to make sure that all of your images are awesome at that point, right? Which you're all going to do. All right, now the back row. All right, let's try the front row again. That was good. That was good. I'm sorry, the front row's winning. Back row, you want to try again? Oh! Oh! They added whistling. Come on, front row. We'll try again later. All right, the live stream's getting antsy. All right, so make sure that you actually set this file, or this configuration inside of your Gradle file so that you don't end up actually bloating images that you've already taken the time to compress. Now, probably one of the biggest things that you can do, though, in terms of file savings, is actually consider replacing your PNGs altogether with vector drawables instead. Now, for those who don't know, PNG files are raster files. They have a big problem in that you need multiple of them in a file to actually get your images. So, we need one at this resolution, and one at this resolution, and one at this resolution, which means in our APK, we're actually ending up at 55K footprint to represent the same visual image at different resolutions. And there's some tricks you can play here with split APKs and upsampling and all this other stuff, but this is the gist of the problem. There's another way to approach this issue, and it's the concept of actually drawing your images with code. So that same picture, what if we took a stab at it saying this? Let's emit a bytecode that actually draws a white background, and then another code that actually draws a red circle. Now, if we could create our custom DSL language and whatnot, we could actually get this into 1 byte per instruction, and actually end up at about 15 bytes to represent the same thing. The result of this is that we can generate those same 3 images at any of these 3 sizes using only 15 bytes of our scheme instead of the 55K that we were using before. This is the concept of vector image formats, right? Basically, we take some sort of stream that represents how to draw primitives on a screen. We actually execute those, rasterizing those primitives to a bitmap in CPU memory. We upload that to the GPU, and then we end up actually drawing that to the screen. The benefit you get here is much smaller file sizes. The downside, though, is you actually trade off time. It takes longer to rasterize these images and get them into memory than it does to actually, say, use the hardware decoder and decode a JPEG. So there's a little bit of a trade-off you have to deal with there. But this is the whole idea behind Google or the Android's vector drawable format. It's a series of instructions that define how to draw paths and colors and gradients and all other sorts of stuff so that you can draw these images at the sizes you need on demand. But the question is, okay, this is fine, this is fancy, I've already got a pipeline of awesome PNGs, and my artists know how to make PNGs, they don't know how to do this vector drawable thing. Come on, bald guy, let's get to the point here. What's really going on? Don't worry. So I decided to run a test. How much could vector drawables actually save me as a developer? To figure this out, though, I needed to take the IOShed application and actually convert all of my images to vector drawables. Well, there's 270 of those things, totaling up to 926K in size. I don't have the time to hand customize all 270 of those images. Thankfully, there's a tool to the rescue. There's a great tool on the internet called POTrace, and this tool's been around a long time. It'll take a bitmap image, which is literally an image with 1 bit per pixel, and actually turn it into a vector format. Raster image to vector format. So I decided to run this on every asset inside the IOShed application, and the results were actually a lot better than I expected, to be honest with you, right? So you can see the top row here is the source, and the bottom row here is the result of the POTrace application. We're pretty close. The first one looks identical. The second one, you can see some rounding. The third one, pretty good. The fourth one, you can see that we're only dealing with shapes, so we lose some color there. And the hexagon is perfect. The hexagon is actually a really cool example here, because that hexagon actually absorbed 6K of our file size at different resolutions. However, the vector drawable vector version was only 961 bytes. So even just running it through here, we saw some wins. The downside, though, is that this is an automated tool, right? I mean, this is only a test. We're just trying to figure out how all this stuff works together. And obviously, there were some failures. We missed some interspersion detail. Obviously, we're not getting the exact font representation, and it just fell over and died on the I/O algorithm, right? The result, though, I think was a good test to figure out what you could save. So running things through POTrace, we actually ended up with only 153 files, because we didn't have to have one for each resolution. And the result was actually 149K. That's 84% reduction in asset sizes by just moving everything to be a vector drawable, which is a pretty good savings. Yes, let's clap. Yes, this man. Yes. You started the clap, sir. You are awesome. Fantastic. Yeah, so 84% smaller, that's a pretty good deal, right? Now, it's worth noting this was just a test. You can't just go run POTrace and convert everything over. I mean, it spits out EPS files, and that's not the same as VD files. And oh, by the way, there's actually a chance that you could optimize stuff further, right? Instead of just importing from SVG, if you did stuff by hand, you may actually be able to get stuff down even smaller than that. But the main point is, you can get a lot of savings here by moving to vector drawables, so make sure you take a look at it. All right, now let's talk about the big images. The big, big images. JPEGs. Who loves JPEGs? Yeah? Yep. I didn't hear anybody in the back. I love the begrudging pause, right? Like, fine. We're just here to stay out of the heat. Pass me some water. This is great. Okay, JPEG files. I gotta tell you, JPEGs they're crazy. One of the most impressive algorithmic systems I've ever encountered. It's impressive, the math that goes into this. Not just from an algorithm perspective, but just the raw math of the situation. Take a look at this. So when you encode a JPEG, here's what's going on. You take your source RGB image, and the first thing that happens is we actually convert it to a separate color space. The reason for this is the human eye, the psychovisual differences in the human eye are less susceptible to the YCbCr color space, or the chroma-lumens color space, right? We're actually more tuned, the human eye is more tuned to see differences in RGBs than we are YCbCr. So the first thing the JPEG does is convert us to that space. The next thing is we actually reduce the size of the CB, the chroma channels, CB and CR channels. Again, the human eye doesn't notice as much changes in that spectrum, so it doesn't worry about it. After that, we actually go through and block up our image and apply the discrete cosine transform. This is magical. If you get a chance to check out the blog post on this, basically the idea of the discrete cosine transform is that any signal can be represented by a sum of cosines. What? It's a thing. It's a thing. Like, these mathematicians sat down and worked that out on paper before computers were awesome. Like, discrete cosine transform is one of the most amazing things I have ever seen. Basically, they can represent any 8x8 block of pixels by summing cosine transforms across a 2D space. That is awesome, right? The output of that is then ran into a quantization phase. The quantization phase just basically takes the output of the basis coefficients and quantizes them down to integers in a subspace that we can actually encode more. They get spent out to the statistical encoding phase, which may be Huffman or arithmetic or whatever your particular flavor of the month is. And then finally, of course, we go to the output JPEG file. Now here's the weird thing. This is awesome. This is totally crazy, right? Way harder than PNG. Then why, when you export an image, you're given like one slider? All of this chaos is hidden behind one slider when you export an image. That's impressive on its own right. Now the question is, what should this value be? This is the JPEG quality. When you export a JPEG, we ask you what quality you want it output at, right? And so the question is, what should this be? Right, so let's take a visual look at what the Photoshop would actually output as. So here's PS12, so this would be 100% JPEG quality, right? 263K. Let's drop down to 11, 10, go to 8. You can start seeing some blocking here. Look right above the red parrot's head. You can start seeing some ringing artifacts. The gradients in the background aren't as solid there. Let's go down to 4. So this is quality 4. You see a lot more ringing artifacts here, right? You can start seeing the quantization artifacts in each 8x8 block, right? And 0. Obviously some color bleeding going on. We're seeing some big stuff there. So the question is, though, what value should I choose? Right? I mean, you can't open every single image and take a look at it and choose the right value. There's just no way we can support that in any sort of real pipeline. The solution is to not. It's to automate the whole process. And for that, I'll get to in another slide. The real solution here is to automate this process and figure it out, but that's actually not what most people are doing. What most people are actually doing here is choosing some value and exporting all of their images at that. The ImageMin project, which is an open source project on the internet, started downloading a bunch of images from all of these social networks and figuring out what their exported quality was, and then put it together in a table. So you can actually see what everyone is exporting things at. Now, the ones with ranges are actually really impressive because it means that they're trying to actually find the right range of things. The weird thing is it's not as scalable as you'd think, right? Like if something happens to be brighter, it's given these values. If it's darker, it's these values. It's a little bit more quantized than dynamic. But the question for your project is, how do we figure this out algorithmically? And for that, I want to introduce Buturgali. This is an open source project made by the compression team in Zurich who loves naming things so that I can't Google for them. Or spell them or pronounce them. So to make sure that you all can pronounce it, we're going to say it together here, okay? This is going to be Bu, Tur, Ag, Li. Buturagli. Okay, now you all can Google this later. In the native language, it means a sweet bread to eat with coffee, but in the GitHub project, it means a way to compare the psychovisual similarity of two images. This is basically a way for us to say, let me take a source image and compress it and see how the human eye responds to the differences between these two. How much error can we actually notice? Now, you may have heard some other terms in the past, like PSNR. Anybody hear that one? Yeah? SSIM? Yeah, these are common, yeah, nice. These are very common things. Think of Butter-Gali in the same fashion of that. The ability to measure two different psychovisual changes as an image changes. Now, the real use of Butter-Gali, the intention that it was made for, was to actually figure out how much we can compress an image before the human eye notices anything. Right? How far can we go before even the smallest perceived visual change occurs? And when you actually use the Butter-Gali library, you'll notice that that actually occurs at the 1.0 level. So when you export at Butter-Gali 1.0, that is where, or when you test it and you get 1.0, that is where the human eye starts to notice artifacts. Anything above 1.0 is chaos land. Anything below 1.0, the human eye can't decipher. Right? So your goal would be like, hey, you know, we have a lot of high-res images, we want high-res images, and we want to find the ideal export. This will help you. But sometimes I don't want perfection, right? Sometimes I want a little bit of compression artifacts in there. Sometimes someone's loading something on a 2G network, or they're sitting on roaming, or they're in the middle of India, and they don't have the right connectivity. I want to give them a worse quality image so it doesn't take them 6 hours to download the thing, right? They don't have to pay for it. So maybe I'm okay going above 1.0. So how would we go about doing something like this? How would we find the right level for some other statistic? And it's actually pretty easy. If we actually take a little Python script here and we run ImageMagick, we can convert a PNG to a JPEG file at some quality, right? We convert that JPEG back to a PNG, so we know we're actually comparing apples to apples here. And then we run those two PNG files through Butter-Gali. And if the score is above some random metric that we've decided based upon artificial intelligence and machine learning for this person in this area on this device, let's just say it's 2.0, randomly, then we return that quality value. So what does this look like? So I ran this on the Parrots images, and you can see really quickly we found that about quality 60, we passed the 2.0 threshold, right? And then it actually was able to dive in a little bit more and get single-step quantization. And actually found that at quality 62, we broke the 2.0 threshold. Let's look at this side by side. This is the 1.0 score and the 2.0 score. The difference is 60K, right? But the Butter-Gali image metric is so nice that you can see very small changes in the 2.0 version. And of course, this is blown up on a screen and on the live stream and all this other stuff. But the main point that I'm trying to get to here is that you don't have to choose one image compression quality for everything. You can actually dynamically choose this and move on. So beyond that, though, there's a couple things that you can do by hand. JPEG, unfortunately, has the same problem that PNG does, right? File save as from Photoshop, 11K for that 16 by 16 pixel block. 11K! Oh. Are you sure your designers aren't doing that? Are you really sure? Think about it. Maybe send a text real quick. Yeah. Save as gets us to 1.1K. Still, that's a 16 pixel by 16 pixel image. The funny thing is, you want to know what's going on here? Extra data, metadata. JPEGs and PNGs have the ability to add block data to your image. So when I'm standing on the Google campus, wandering around because it's Google I/O, and I take a picture of the gator, this is how my image sharing service know that where I was standing. There's blocks that they can insert into your JPEG files that have this location-based information. And that bloats your image. And if you're not properly removing this stuff as an image-serving application, that means every other user who's downloading it is grabbing this extra bloated data. Obviously, that's not a good idea. So let's talk about, that's obviously block removal, but there's a bunch of other places that we can optimize here, right? We can change how we're downsampling, we can improve the way that the DCT coefficients are handled, we can improve the way we quantize, and we can just apply a better statistical encoder, right? Great news, folks. You don't got to worry about any of that. Everybody's already got it solved. Googling for this brings you a pretty good handful of algorithms and tools that you can put right into your tool chain. The first two here, JPEG Mini and MozJPEG, actually go to find another lossy compression variant. So they'll degrade the image quality of your image to get you just a little bit farther and a little bit more savings, right? On the other two, CJPEG and PACJPEG are lossless. They're going to try to improve those quantization and statistical encoding stages so that you don't actually lose any bits. The interesting thing is that PACJPEG actually works more as a post format than anything. It'll actually take your JPEG and encode it in its own format so we can get it even smaller than that. And of course, you've got a lot of web solutions that you can find too, where you upload your image to some API or some service, it'll do everything on the back end and send it to you. I don't care what you use, pick one, right? And don't let your designers hit save as from Photoshop, right? Any of these will work. Pick one, test it out, see how it works. Send me a tweet, let me know how it happened, right? One thing though, I gotta say, this one's really cool to do by hand, and I've only got a couple minutes, so I'm gonna try to go through this fast. 2 images here, top one 175, Colt modified 82K on the bottom. What we're doing here, remember that the first thing that JPEG does is split your image into a different color space, right? Because the human eye is more perceptible to some loss than others. So what we do here is we actually, in Photoshop, split this to lab color mode, right? Which is luminance and then AB channels. We select the areas of high contrast inside of the AB channels, and we actually just go File, Blur. What we're doing here is we're actually reducing the number of unique colors, the amount of noise in these chroma channels, so that when the JPEG codec comes back through, there's less information there that it has to find unique, and you're actually going to get better compression as a result. So this simple technique, going through, hand optimizing some of this stuff, can actually save you, what was this, 2x or 50% savings on a file? That's, if you're still serving 1 million files a day, that's huge, right? All right, let's get to the final one here. WebP. Fans of WebP? Yeah? Yeah. WebP, I gotta say, is as impressive as JPEG is, WebP it's in its own league. I've done compression for a long time. It's in its own league. I mean, on one side, you've got a whole suite of algorithms that applies so it can keep up with the lossy type of compression that JPEG does. On the other side of it, it's got this whole separate filtering and prediction policy so it can do lossless encoding, just like PNG. It's even got some LZ77 and dictionary encoding in there so it can do that. The result is pretty simple. Across the board, all of these optimizations and techniques make it competitive with both PNG and JPEG everywhere, and it supports all of these features as well. And in most time, it's actually winning if you check out those. So you get smaller file sizes, you get more features in those file sizes, and it's supported natively on Android, which is awesome. Round of applause for that, right? Okay, now let's get real for a minute. I know we laughed at gummy bears and had a clapping war, but let's get real. Can we get real? Round of applause for getting real. Yeah? Weirdest applause request ever. If there's one thing you remember, if some bald guy got on stage at Google I/O, I was hiding in a tent trying to get out of the sun, and he yelled at me for an hour, but I remembered one thing. It's this. This is one thing. This is all I'm asking you to remember. That's it. Nothing else, just this, okay? This diagram. When you're choosing what kind of image to make, the decision on the format is super important. The first thing you have to ask yourself is, can this image be a vector drawable? If yes, make it a vector drawable. Done. Easy. Go to lunch. If no, ask yourself, do I support WebP? If yes, make it a WebP. Go to lunch. You're done for the day. Good job. Peer bonus. Sweet. If you don't support WebP, ask yourself, does it need transparency? If yes, obviously you got to use PNG for that. If no, you got to ask yourself, is it simple or complex? Remember, PNG optimizes and compresses better in areas of very self-similar pixels. So the more photorealistic an image, the worse PNG is going to compress it. The more simpler an image, the better PNG is going to compress it, right? If it's complex, we're going to go to JPEG. Now, if we end up at PNG, we want to make sure that we're running a tool on it, reducing colors, trying to make it indexed, and hand optimizing it in places where we need to for hero assets. Same thing with JPEG. Use a tool, correct the quality, and hand optimize where you can. I love that everyone's taking pictures. This is live streamed. You can get this later. In fact, if you check out the Spaces application, I'll put this up later. Put your phones down, you're good. I'm flattered that you're taking a picture of me, but I can pose. Anyone want a picture of the pose? No? Nobody? Oh, some. Awesome. Oh, I need to be over here? Okay, no, we gotta get back to it. The AV people are getting mad at me. Sorry. Okay, most importantly though, this one simple thing. Profile your code. Profile your code. Profile your code. Before you make any decisions, before you make any performance changes, before you change your format, before you put bits on the wire that your users are going to have to pay to download, profile it. Make a decision based upon evidence and data and the best thing for your users. Do not go lazily into these decisions because they have huge ramifications for the people who love you and your applications. Profile it. In some cases, JPEG's going to be better than PNG. In some cases, WebP is going to be the best option. In some cases, it's going to load too slow, and you're going to want to use a JPEG. In every single situation, profile your code. Find the sweet spot. Optimize for your users in every case. And thank you so much for coming to this session. My name's Cole McCandless.